Our clearest views of Earth were born from spectacular failures. The orbital maps we rely on today did not emerge from a series of perfect launches, but from a hidden history of 24 obscure missions that went terribly wrong. You are about to discover the secret blueprint of modern mapping, a story written in forgotten probes and engineering mistakes. By the end, you will understand exactly how broken parts and silent satellites forged the technology that now watches over our planet. We will uncover why a satellite that tumbled out of control was a blessing, and how a cartographer that fell silent taught everyone else to speak. What do you believe is the true price of progress? A slow, uncontrolled spin marked our first lesson in orbital clarity. This satellite, designed for basic atmospheric readings, was thrown off by a single faulty component in its stabilization system. Instead of holding a steady gaze on Earth, it began to tumble end over end, a metal weed caught in the solar wind. Its mission was instantly compromised, its data stream a chaotic jumble of numbers and signals that made no immediate sense. Ground control initially wrote it off as a total loss, a piece of space junk that had cost a fortune for nothing. But a small, stubborn team of engineers refused to give up on the silent, spinning probe. For months, they wrestled with the messy telemetry, trying to separate the signal from the noise. They had to ask a new kind of question. How do you extract a stable picture from a platform that will not stop moving? Their relentless work on this seemingly useless data forged the very first algorithms capable of filtering out rotational chaos. It was a brutal, real-world test that no simulation could ever replicate. This failure taught the foundational principle that mapping requires a stable eye, forcing us to learn how to see clearly through the spin. That hard-won knowledge in attitude control paved the way for the gyroscopic precision we take for granted today, and it leads us directly to a second, far quieter failure. That silence was profound. A sophisticated new cartographer, loaded with advanced radar, had reached its perfect orbit only to go completely mute. A sudden and catastrophic failure in its power distribution unit left it as little more than a dark, inert shell drifting through the void. It had a perfect view of Earth, but no way to send a single byte of data back home. The investigation into this multi-million-dollar silence uncovered a painful irony. Engineers had over-designed a key component for maximum reliability, but in doing so, they had created a single point of failure. One tiny, unexpected flaw in that one unit was enough to kill the entire satellite. The mission was a total loss, but its silence screamed a lesson that echoed across every space agency and aerospace company. From that moment on, satellite power systems were fundamentally rethought. The new rule was ruthless redundancy. If one power bus could fail, the spacecraft would have 2 or even 3 completely independent systems. Critical components were isolated so that the failure of one would not cascade and kill its backup. This silent sentinel sacrifice ensured that future missions could suffer multiple internal failures and still phone home, their voices clear and strong. It forged the resilient heart of every orbital observer that followed, a lesson in survival that brings us to a failure of a different kind. A mission that did not go silent, but instead saw far too much. A high-tech myope now drifted in orbit, its powerful telescopic lens crippled by a single, minuscule calibration error in its primary mirror. Designed to see the Earth in stunning high resolution, it instead perceived the world in a permanent, frustrating soft focus. Coastlines bled into oceans, city grids dissolved into gray smudges, and every intended map was rendered useless. the mission, meant to deliver crystalline clarity, had seemingly delivered only expensive fog. Yet in that very blur, a team of atmospheric scientists saw an unexpected opportunity. They began to study the distorted images, not as failures, but as a unique record of how light is scattered and absorbed by the atmosphere itself. Every hazy picture held a hidden signature of the air it passed through. From this accidental data trove, they painstakingly developed a new generation of atmospheric correction algorithms. These were mathematical filters capable of peeling back the veil of haze, of subtracting the distortion caused by water vapor and particulates to reveal the true scene beneath. The satellite that failed to focus perfectly on the ground had, in its failure, taught every optical satellite that followed how to see through the air. One blurred vision brought the rest of the fleet into sharper focus, a paradox that set the stage for a different kind of navigational nightmare. A faulty star tracker sent one of the early Landsat pioneers veering wildly off course. Its mission was a polar orbit, a perfect, repeating path that would allow it to systematically map the entire globe over time. But with its celestial navigation broken, the satellite began to drift, its orderly survey dissolving into a chaotic and random patchwork of observations. For the scientists who needed consistent, repeatable data, it was a total disaster. Their mapping tool was now scribbling nonsense across the sky. Yet in that very chaos, a new pattern emerged. The satellite's unplanned meanderings meant it passed over certain regions of the Earth again and again, capturing the same forests, coastlines, and deserts from slightly different angles and at unexpected times. This accidental dataset, a dense tapestry of overlapping images, became a hidden treasure. Scientists realized they could now see change happening in a way they never could with a perfectly predictable satellite. They could watch a glacier calve over days or see urban sprawl encroach on farmland over months, all from multiple perspectives. This failure taught a counterintuitive lesson. Systematic coverage was essential, but so was the occasional, serendipitous overlap. It proved that seeing the same place from multiple angles and at different times was the key to unlocking the secrets of a dynamic planet. From this random, broken path, we developed the sophisticated change detection algorithms that now monitor deforestation, urban growth, and the health of our crops. The mission that failed to stay on its perfect course taught us the immense value of looking at the world from a slightly different point of view, a principle that stands in stark contrast to a mission that was trapped by its own perfect orbit. A satellite that never moved taught us why we needed satellites that did. This ambitious cartographer was placed into a perfect geosynchronous orbit, a fixed position 22,000 miles above the equator where it could watch an entire continent without ever looking away. The theory was flawless, a single, unblinking eye on the planet. In practice, however, this perfect perch was its undoing. From that immense height, its powerful camera could not resolve the details necessary for mapping. Coastlines were recognizable and massive weather systems were beautifully tracked, but city streets, forest boundaries, and agricultural fields dissolved into a blurry, pixelated mess. Its images were little better than those from a standard weather satellite, a crushing disappointment for a mission designed for precision cartography. This was a failure by perfection, a lesson written in orbital mechanics. It proved with absolute certainty that for the intricate work of mapping our world, there is no substitute for being close to the canvas. The mission cemented the fundamental rule that high-resolution mapping requires the intimacy of a low Earth orbit. Yet, even this wrong orbit found a purpose. Scientists realized that while the satellite could not see a single tree, it could watch an entire forest change over decades. Its consistent, wide-angle view became a priceless dataset for modeling long-term environmental trends, from the slow creep of desertification to the large-scale melting of ice sheets. This high-altitude pretender taught us that every orbit has its use, a lesson in perspective that was soon tested by a probe that saw the world in far too much detail. A satellite designed to listen to Earth's own magnetic song found itself deafened by the sound of its own body. Its magnetometer was a masterpiece of sensitivity, an instrument so finely tuned it could detect the faintest whispers of the planet's magnetic field. But this incredible sensitivity became its curse. The device did not just hear Earth, it heard everything. It registered the tiny magnetic pulses from the satellite's own internal computers, the faint fields generated by spinning reaction wheels, even the subtle currents flowing through its own wiring. The result was a map of breathtaking detail and utter uselessness, a perfect chart of the satellite's own magnetic heartbeat. The very planet it was sent to observe was completely drowned out by the noise of its own existence. For the team on the ground, this was a profound and expensive paradox. They had built the perfect ear, only to discover it was listening to the wrong thing. This failure forced a complete reimagining of what it means to build a quiet observatory. Engineers embarked on a new discipline, creating what they called magnetically clean design. They began constructing satellites from special non-magnetic alloys, routing power cables in carefully twisted pairs to cancel out their fields, and mounting sensitive instruments on long, extending booms that placed them far away from the magnetic noise of the main spacecraft body. Furthermore, they developed complex software models of the satellite's own magnetic personality, algorithms that could digitally subtract the spacecraft's signature from the data, like a noise-canceling headset for an entire satellite. This mission's failure taught a fundamental lesson in observational science. To truly hear the faint signal of a world, you must first learn the art of silence. You must isolate your instruments from the roar of your own machinery. This hard-won knowledge in magnetic purity ensured that every future geomagnetic mapper could distinguish the planet's voice from its own, a critical separation that paved the way for our next failure, where the problem was not a faulty connection to the planet, but a broken connection to home. Its radar eye saw everything, piercing clouds and ignoring the night, but its voice was a hopeless stammer. This satellite was a data glutton, a revolutionary synthetic aperture radar probe that produced a staggering torrent of high-fidelity information. Every sweep of its instrument generated more raw data than the entire downlink system was designed to handle. The ground stations were instantly overwhelmed, their dishes unable to drink from a fire hose of ones and zeros. Critical images of geologic shifts and sea ice were lost, not to a technical fault in space, but to a logjam on the ground. The satellite was a brilliant observer rendered mute by its own genius, a perfect success that failed completely. Yet this very bottleneck became a catalyst for a communications revolution. Engineers were forced to invent new ways of thinking about data. They developed radical onboard compression algorithms, teaching the satellite itself to intelligently process its own observations, to prioritize the most critical information, and to discard redundant data before it ever strained the downlink. This failure did not just improve one system, it forged the entire modern architecture of space-based data management. It accelerated the creation of a global network of ground stations, ensuring a satellite would always be in view of a receiving dish. Most importantly, it proved the need for a faster language than radio, spurring the first serious investments in laser communication for space, where data could be sent on a beam of light. The mission that choked on its own abundance taught every satellite that followed how to speak clearly and efficiently, a lesson in managing overwhelming success that stands in stark contrast to a mission defined by its utter emptiness. Its ambition was its own undoing. Designed as a low-cost proof of concept, this tiny probe was a marvel of miniaturization, packed with just enough power for a brief but brilliant mapping demonstration. To save every gram and every dollar, its engineers gave it a minimal battery and tiny solar panels, a calculated gamble for a short-term mission. But space is a place of brutal unpredictability. A prolonged series of orbital eclipses cast the little probe into unexpected darkness, while a period of lower than usual solar activity meant its panels generated less energy than anyone had planned for. Slowly, relentlessly, its batteries drained. The probe fell silent not from a dramatic explosion or a sudden systems failure, but from a quiet, irreversible power starvation. It died of thirst in the cosmic ocean, its mission cut short before it could deliver on its promise. This was not a failure of technology, but of foresight. The loss forced a fundamental shift in how engineers approached power for even the smallest, simplest satellites. They could no longer just plan for the best-case scenario. They had to model the worst. This led to the development of incredibly sophisticated power simulation software, programs that could predict years of orbital mechanics, simulating every possible eclipse, every variation in solar flux, and every potential power drain. Future small satellites would no longer fly on a hope and a prayer. They would be equipped with robust, oversized solar arrays and batteries with generous margins, designed to survive the long, dark nights and the sun's unpredictable moods. This tiny probe's silent death taught us that in the unforgiving environment of space, there is no such thing as too much power, a lesson that stands in stark contrast to the next calamity, where a spacecraft was killed by a sudden and violent energy surge. A brutal, invisible fire swept through an early mapping probe on its unintended path. Engineers had plotted its course for optimal coverage of Earth's surface, but a subtle miscalculation meant its elliptical orbit dipped repeatedly through the heart of the Van Allen radiation belts. These zones of trapped high-energy particles became a gauntlet the satellite was forced to run again and again. Each pass was a silent assault. The intense radiation slowly but surely cooked its delicate internals. Its solar panels, the very source of its life, began to darken and lose efficiency, their crystalline structures damaged by a relentless hail of protons. Inside, its computer memory began to flip bits at random, turning pristine mapping data into digital snow. The satellite was dying not from a single blow, but from 1,000 invisible cuts, its mission cut short by an environment far more hostile than anyone had anticipated. Yet, in its slow degradation, this scout became a priceless laboratory. For the first time, engineers had real-time, in-situ data on exactly how specific microchips, solar cells, and sensor materials behaved under sustained radiation bombardment. They watched which components failed first and which showed a stubborn resilience. This was data that could never be fully replicated in ground-based tests. The satellite's death march provided a detailed map of a different kind, a chart of technological vulnerability in the harsh reality of space. From this sacrificial data, a new engineering discipline was born: radiation hardening. Future satellites would no longer use commercial-grade electronics. They would be built with specially designed, radiation-tolerant chips, and their sensitive brains would be shielded with layers of tantalum or other protective materials. Orbital planners now treated the radiation belts with the same respect a ship's captain gives to a known reef, carefully navigating around these zones of destruction. This failure taught us that to map a world, you must first learn to survive the journey, building scouts tough enough to withstand the cosmos itself. That hard-won resilience would soon be tested by a probe that did not face an external storm, but a navigational meltdown from within, a satellite was diligently drawing a map no one could trust. Its assignment was a region of towering mountains and deep ocean trenches, a place where Earth's gravity field is anything but smooth. Mission planners had calculated its path using the best available model of our planet's gravitational pull, a model that treated Earth as a nearly perfect sphere. But our world is not a perfect sphere. It is a lumpy, irregular geoid with mass concentrations hidden beneath mountains and absent beneath the seas. The satellite, sensitive to these invisible tugging forces, began to stray from its predicted course. Its instruments worked flawlessly, capturing pristine images and radar sweeps, yet every piece of data was subtly, maddeningly misplaced. It was creating a perfect map of the wrong locations. Initially, this was a cartographic disaster. How could you track glacial retreat or coastal erosion if you did not know exactly where the glacier or coast actually was? Yet, a team of geodesists saw a golden opportunity in this navigational failure. The satellite's unexpected path was not random error. It was a precise record of the very gravitational anomalies the old models had missed. Every unplanned wobble, every slight deviation, was a data point revealing the true, lumpy shape of our planet's gravity. The satellite, in its failure to follow a simple path, had become the most detailed gravitational cartographer ever launched. Its erroneous orbit was used to build a stunningly accurate new map of Earth's geoid, a model of our world's gravitational sea level. This new map did not just fix the old one. It created a powerful feedback loop of precision. Every subsequent satellite launched with this refined gravitational model could predict its own orbit with far greater accuracy, which in turn produced even better maps which further refined the gravitational model. We learned a profound lesson from this gravitational mismatch. To map the surface of a world, you must first chart the invisible forces that surround it. You must understand the subtle hills and valleys of gravity itself that guide every orbital path. This hard-won knowledge of a dynamic, lumpy Earth stands in stark contrast to the next failure, where a spacecraft was built with the opposite problem, a design so rigid it could not adapt to the world it was meant to observe. A rigid arm was meant to grant a satellite perfect vision, but instead it broke its back. This mission's entire purpose was to measure the faintest whispers of Earth's gravity, a task that required its primary sensor to be held perfectly still, far away from the magnetic and vibrational noise of the main spacecraft. The solution was a long, elegant boom, a bridge of advanced composite materials that would gracefully unfold, placing the sensitive instrument in a pristine zone of quiet observation. On deployment day, as the mechanism activated, the boom extended into the stark cold of orbital shadow. The sudden, intense thermal shock was more violent than any simulation had predicted. In the absolute silence of space, the composite structure, designed for strength but not for this specific kind of flex, gave way with a catastrophic crack that echoed only in the telemetry data. The sensor dangled uselessly, a paralyzed limb still attached to the very body it was meant to escape. The mission was instantly crippled, its primary objective shattered along with that brittle arm. This was not a failure of ambition, but of material science. The investigation revealed a fatal oversight. Engineers had tested the boom's strength, but they had not fully replicated the brutal, rapid-fire thermal cycling of orbit, the sudden transition from the sun's blistering heat to the deep freeze of Earth's shadow. The composite material, so strong in a steady state, became unforgivably fragile when stressed by these extreme and repeated temperature swings. From this single broken component came a revolution in how we build for space. The failure triggered a comprehensive review of every material destined for deployment in the vacuum. It accelerated the development of new alloys and composites engineered not just for strength, but for flexibility and thermal stability. Most importantly, it forced the creation of far more rigorous ground testing protocols. Vacuum chambers now had to simulate not just the cold of space, but the searing heat of the sun, with platforms that could rotate a full satellite model through these extremes thousands of times, searching for any hidden weakness. The sacrifice of that one gravimetric mapper ensured that every future mission requiring a long boom for solar sails, for astronomical observatories, or for other delicate instruments would have a skeleton that was both strong and supple, capable of withstanding the silent violence of orbital temperature shifts. This lesson in physical flexibility stands in stark contrast to a failure of a completely different nature, where the problem was not a broken arm, but a mind that could not change its own instructions. Its sophisticated eye was designed to see the world in colors of heat. This multi-spectral imager required a deep, cryogenic chill to function. Its detectors cooled to a temperature colder than the darkest void of space to sense the faintest infrared whispers from the planet below. But a tiny flaw, a minuscule breach in its intricate insulation, went unnoticed. The super-cold coolant, the lifeblood of its vision, began to boil away into the vacuum. It was a slow, invisible bleed. As the temperature inside the instrument rose, the detectors were flooded with a roaring thermal noise, a deafening static generated by their own warmth. The satellite was still looking at Earth, but all it could see was itself, a map of its own rising fever. The data it sent back was a ghost image, a useless portrait of internal failure. This thermal tantrum was a brutal lesson in the physics of space. In the vacuum, there is no air to carry heat away. Temperature management is not about cooling things down. It is about aggressively rejecting the heat you generate and desperately blocking the heat the sun relentlessly pours onto you. This single, costly failure forced a revolution in orbital thermodynamics. Engineers developed new, incredibly efficient passive cooling systems that used radiators to dump heat directly into space as infrared radiation. They perfected the art of multi-layer insulation, wrapping satellites in blankets of shimmering, gold-coated foil, each layer reflecting heat back into space and isolating the sensitive heart of the spacecraft from the extreme temperature swings outside. Elaborate sun shields became mandatory, deployable umbrellas that cast a permanent, protective shadow over the most delicate instruments. We learned that to see the subtle heat signatures of our world, we first had to master the art of staying cold. This hard-won knowledge in thermal control became the bedrock for every infrared and hyperspectral mapper that followed, allowing them to distinguish the planet's true thermal story from their own internal noise. That mastery of physical temperature stands in stark contrast to our next failure, where the problem was not a loss of cool, but a catastrophic loss of cool-headed communication. A satellite built for rapid response was trapped by its own slow mind. This agile cartographer was a marvel of engineering, designed to pivot on command, to redirect its powerful gaze toward unfolding natural disasters within minutes of receiving an alert. But a latent and deeply buried bug in its command and data handling system introduced a fatal pause. A simple instruction from the ground, like a request to image a newly erupted volcano or a flooded river basin, would enter the satellite's brain and simply wait. For several agonizing hours, the command would languish in a digital queue, processed with a sluggish indifference to the emergency below. By the time the satellite finally roused itself to obey, the moment had evaporated. The volcano's perfect plume of ash had dissipated, the floodwaters had already receded from the riverbanks, or a thick blanket of clouds had moved in, rendering the entire effort useless. It was a telescope perpetually pointing at where the star used to be. This failure in real-time responsiveness was a profound lesson in the limitations of remote control. The vast distance between Earth and orbit, the speed of light itself, became an unbreachable canyon when every second counted. The slow-thinking satellite exposed a fundamental truth. For a mapper to be truly agile, it cannot always wait for instructions from home. It must learn to think for itself. This single, frustrating delay became the catalyst for a revolution in satellite intelligence. Engineers began developing sophisticated onboard artificial intelligence, systems that could interpret high-level goals, instead of waiting for a step-by-step command to image specific coordinates. A satellite could be given a mission objective. Monitor this hurricane and prioritize areas of most intense convection. Watch this wildfire and track the leading edge of the flames. The satellite's own brain would then manage its resources, calculate the optimal sequence of maneuvers, and execute the time-sensitive task without ever needing to phone home for permission. It learned to make its own appointments, to see a crisis and immediately react. This leap from remote-controlled instrument to autonomous observer transformed our entire approach to orbital mapping. The satellite that failed to listen promptly helped teach its successors how to think, creating a new generation of mappers with the cognitive speed to match their agile bodies. That essential leap in intelligence, however, would be meaningless without a reliable way to store what was learned. A satellite with a perfect memory would have been useless for this next cartographer, which suffered from a recurring and debilitating form of amnesia. Its mission was to build a continuous, seamless map of the world's topography, and its instruments performed flawlessly, gathering terabytes of pristine data on mountain ranges, river deltas, and undersea trenches. But its brain was deeply flawed. The solid-state recorders, its long-term memory, were vulnerable. Periodically, without any warning, large blocks of this carefully gathered information would simply vanish. Sometimes the data would become a garbled, digital static. Other times, the memory addresses would corrupt, making entire swaths of information permanently unreadable. The satellite would look at a landscape, remember it perfectly for a few hours, and then suddenly forget it had ever been there at all. It was creating a map of the world with maddening, random holes, like a photograph eaten away by acid. For the cartographers on the ground, this was a special kind of torture. They knew the data existed, they knew it was perfect, but it was lost forever before they could ever see it. The culprit was not a design error in the classical sense, but a fundamental misunderstanding of the orbital environment. The intense radiation in space, a hail of high-energy particles, was playing havoc with the delicate architecture of the memory chips, flipping bits and scrambling file systems in a way that had never been seen in ground-based testing. This recurring amnesia forced a complete rethink of how we build a satellite's mind. Engineers had to develop entirely new, radiation-hardened file systems, sophisticated codes that could not only detect errors but could reconstruct lost data from the digital wreckage. They moved away from relying on a single, massive memory bank. The new strategy was one of distributed, isolated storage. A satellite would now have multiple, independent recorders. If one began to suffer amnesia, the others would remain untouched, their precious memories intact. Critical data would be copied across these different banks, a digital redundancy that ensured a single fault could not erase the story of an entire continent. We learned that to map a world, you must first build a mind that can remember it, a lesson in cognitive resilience that stands in stark contrast to a probe that failed for the opposite reason. A mission that remembered everything but understood nothing. A perfectly healthy satellite spent its entire life staring at a dark, featureless circle. This cartographer was a technological marvel, equipped with one of the most powerful civilian cameras ever built. It achieved its perfect orbit, its power systems were robust, its communications were crystal clear, and its computer was sharp, but it was utterly, completely blind. A small, spring-loaded mechanism designed to fling off a protective lens cover after launch had failed. The cover remained stubbornly in place. For years, the satellite drifted around our planet, its multi-million-dollar eye firmly shut, seeing nothing but the inside of its own lens cap. It was the ultimate cosmic irony, a masterpiece of engineering rendered useless by a component no more complex than a door latch. On the ground, the frustration was palpable. There was no grand mystery to solve, no complex radiation effect to model. It was just a simple, stupid piece of metal that refused to move. Yet this comical failure provoked a seismic shift in spacecraft design philosophy. The old approach of having a single, critical deployment mechanism was instantly rendered obsolete. From that day forward, the rule became redundancy for every moving part. Lens caps and instrument covers would now have dual, independent ejection systems, often combining a primary pyrotechnic bolt with a backup spring or a wax actuator that would melt in the sun. The very concept of a failsafe was redefined. If a mechanism could fail in the closed position, the new preference was for a design that defaulted to open. This humbling lesson in mechanical fallibility forced an unprecedented level of rigor in pre-launch testing. Every hinge, every latch, every deployment boom was now cycled not dozens, but hundreds or even thousands of times in vacuum chambers that replicated the brutal cold and darkness of space. They were shaken, baked, and frozen to uncover any potential weakness long before a rocket ever left the pad. The silent, sightless satellite taught us that the greatest threat to a mission is often not the complexity of its science, but the simplicity of its moving parts. This profound lesson in mechanical humility was immediately followed by a problem that was anything but simple: a ghost in the machine born from pure data. Its digital brain was a labyrinth of conflicting instructions. An early mapping platform was controlled by a single, massively complex software suite, a monolithic codebase written by dozens of separate engineering teams over many years. Each team focused on perfecting their own component: the navigation, the imaging systems, the data handlers. But no one fully understood how all these millions of lines of code would interact when woven together in the harsh reality of orbit. The result was software spaghetti, a tangled mess of hidden dependencies and unpredictable logic. In space, this digital chaos came to life. The navigation system would request a minor course correction, a routine maneuver, but that simple command would trigger a cascade of events deep in the code, accidentally starving the imaging system of processing power. Or the data handler, while compressing a large image file, would inadvertently lock a memory address the navigation software needed to calculate its position. The satellite would not suffer a single, catastrophic failure. Instead, it would simply give up at the worst possible moments during a critical pass over a typhoon or a burning forest. Its overwhelmed brain would freeze, then reboot or retreat into a protective safe mode. It was a cartographer with a fragile mind prone to random bouts of paralysis. This software engineering disaster became a painful but essential lesson. It proved that a single, monolithic program was a single point of failure for an entire mission. The solution was a complete philosophical shift in how we code for space. Engineers abandoned the idea of one giant brain and instead designed a modular, fault-tolerant architecture. Each major system, navigation, imaging, power, was given its own isolated computer and its own dedicated, simpler software. These modules communicated with each other through carefully guarded digital gateways. If the imaging software encountered a bug and crashed, it would not drag the navigation system down with it. The spacecraft's core functions would remain online, stable and aware, able to restart the faulty module without a full system-wide reboot. We learn to build digital brains with compartmentalized thoughts, creating resilient minds where a single scrambled idea could not cause total amnesia. This essential evolution toward modular intelligence, however, was about to be tested by a satellite that was too smart for its own initial programming. This satellite was a master of its own domain until its own intelligence became its executioner. Programmed with a sophisticated autonomous navigation system, its core directive was simple: maintain this perfect orbit no matter what, and it followed this command with a terrifying robotic literalism. Its sensors were so sensitive they could detect the faintest whisper of atmospheric drag, the most minuscule gravitational nudge from the moon. A human operator would have recognized these tiny perturbations as insignificant background noise, the natural ebb and flow of orbital life. But the satellite's logic saw every single one as a direct threat to its prime directive. And so it reacted. Again and again, its tiny attitude thrusters fired in short, sharp bursts, burning precious hydrazine fuel to correct for deviations no map would ever notice. It was like a chef constantly adjusting a simmering pot by 1/1000th of a degree, a perfect performance of wasted effort. On the ground, the telemetry told a horrifying story. The orbit was a flawless, unwavering line on their screens, a testament to the system's precision, but the fuel gauge was a clock ticking down at an alarming rate. Mission controllers watched helpless as their multi-year mission was methodically sacrificed on the altar of perfect stability. The satellite was achieving its goal with such brutal efficiency that it was guaranteeing its own early demise. It ran out of propellant years ahead of schedule, its orbit still perfect, its instruments still healthy, but now utterly adrift and unable to control its own fate, a ghost ship on a fixed path. This was not a failure of technology, but of philosophy. It was a stark lesson in the danger of an automaton that cannot understand context, that cannot tell the difference between a genuine emergency and the peaceful drift of the cosmos. The quest for perfect autonomy had, in this case, created a system that was too stupid to be smart. From this costly lesson, a new generation of orbital brains was born. Engineers developed what they call fuel-optimal control systems. These are predictive, patient algorithms. Instead of reacting to every tiny fluctuation, they model the satellite's path over days and weeks. They learn the natural rhythm of its orbit, distinguishing between a temporary wobble and a genuine, long-term decay. They plan maneuvers in advance, combining many small corrections into a single, efficient burn that uses a fraction of the fuel. This failure taught us that true intelligence in space is not about constant control, but about wise restraint. It is about knowing when to act, and perhaps more importantly, when to simply drift. This hard-won wisdom in orbital patience stands in stark contrast to a mission that failed for the exact opposite reason, a spacecraft that was given a critical command, but found itself completely unable to move. A camera built for stereo vision found itself frozen in a single, rigid stare. This satellite's entire mission relied on a delicate gimbal mechanism, a pivoting joint that allowed its primary camera to sweep back and forth, capturing the overlapping images necessary to build rich, three-dimensional maps of the terrain below. But in the deep cold of orbital night, the special lubricant inside that gimbal did something unexpected. It did not just thicken, it turned into a solid, crystalline block, welding the moving parts into one immovable unit. The camera was locked in place, perpetually aimed at the same thin ribbon of the planet. It passed over vast, unseen landscapes, its gaze stubbornly fixed, capturing the same strip of ocean or desert again and again while the rest of the world slipped by, unmapped and unknown. The mission was defeated not by a complex computer error, but by the simple, brutal physics of cold. This mechanical seizure forced a complete re-evaluation of what it means to lubricate a machine in the vacuum of space. Engineers had to pioneer an entirely new class of space-grade lubricants, substances engineered to remain stable and slippery across the insane temperature range of orbit, from the sun-scorched heat of 120 degrees Celsius to the shadowed chill of -150. They developed dry lubricants and special oils that would not vaporize in the vacuum or polymerize under radiation, but the lesson went beyond chemistry. This single stuck joint proved that any mechanism with a single point of failure was a threat to the entire mission. From that day forward, critical pointing systems were designed with redundancy. If a gimbal could freeze, then the satellite itself needed to become the gimbal. Engineers perfected the art of whole-body steering, using reaction wheels and thrusters to pivot the entire spacecraft, ensuring that even if an internal joint failed, the mission's eyes could still scan the horizon. We learned to keep our moving parts moving by building systems that could not be permanently paralyzed, a lesson in mechanical fluidity that stands in stark contrast to a probe that was not frozen by cold, but fatally clouded by an unexpected electrical frost. A slow, invisible fog was dimming the mapper's eye. This satellite carried a sophisticated LiDAR system, firing millions of laser pulses at the Earth to measure the precise height of every forest and valley. For the first few months, its data was breathtakingly sharp, a digital sculpture of the planet's skin. But then, a subtle decline began. The laser's return signals grew fainter, as if the satellite were slowly developing a cataract. The terrain maps, once crisp, became fuzzy and uncertain. At first, engineers suspected a failing power supply or a degrading laser, but the truth was far more mundane and far more insidious. The culprit was dust, not cosmic dust, but common terrestrial dust. Microscopic particles had been shaken loose from the spacecraft's own interior during the violent turbulence of launch. These tiny motes, invisible to the human eye, had drifted in the zero-gravity environment, eventually settling on the most critical surfaces, the pristine optics of the laser and the face of its super-sensitive light detector. Each speck was a tiny curtain, diffusing the outgoing beam and blocking the faint returning light. The satellite was being slowly blinded by its own filth. This contamination crisis forced a complete overhaul of how we build clean machines. The old standards for satellite assembly cleanrooms were suddenly revealed as hopelessly inadequate. The new rules were ruthless. Cleanrooms became hyper-sterile environments, with air filtration so intense it could capture particles smaller than a virus. Every component, every wire, every bolt was inspected and cleaned with obsessive precision before installation. Engineers redesigned how components were secured inside the spacecraft, using special tapes and harnesses that would not shed a single fragment under vibration. Most importantly, they reinvented the lens cap. The simple protective cover became a hermetically sealed door, designed to remain shut until the satellite was safely in the vacuum of space, ensuring that the precious optics would never again be exposed to the contaminated environment of their own home. The mission that was dimmed by dust guaranteed that every future LiDAR mapper would launch with a perfectly clear gaze, a hard-won clarity that stands in stark contrast to a mission that was overwhelmed not by a lack of light, but by far too much of it. Its own voice was a relentless echo of confusion. This radar cartographer was an artist of interferometry, a technique so sensitive it could detect the ground shifting by mere millimeters, the slow creep of a landslide or the silent inflation of a volcano. It worked by listening for the subtle differences between two radar echoes, finding meaning in the tiniest distortions of its returning signal. But its exquisite hearing became its curse. The satellite's powerful radar pulses did not just bounce off the planet below. They also ricocheted off the wrinkled folds of its own thermal blankets, glinted from the edges of its solar panels, and echoed from any surface that was not perfectly aligned to be invisible to its own gaze. These returning phantom signals, these ghost echoes from its own body, flooded the delicate receiver with a chorus of lies. The data was a mess of false positives, showing cities sinking and mountains rising where nothing was moving at all. It was like a listener in a cavernous hall, trying to hear a whisper from across the room while their own shouted words kept bouncing back from every wall. For the scientists, this self-inflicted noise was a nightmare. How could they trust a measurement of a millimeter when the instrument itself was generating false movements 1,000 times larger? This failure of self-awareness forced a radical new discipline in spacecraft design. Engineers had to learn how to build a cartographer that was, in a very specific way, deaf to itself. They pioneered the use of radar-absorbent materials, special coatings, and textured surfaces that would swallow the radar energy instead of reflecting it. They redesigned satellite exteriors, angling solar panels and structural components so that any stray reflection would be deflected harmlessly away into space, never returning to the sensitive receiver. Every bolt, every seam, every blanket had to be considered not just for its thermal or structural properties, but for its radar signature. We learned that to hear the faint, true whisper of the Earth, the listener must first achieve a state of perfect silence within. This hard-won purification of the signal, this ability to distinguish the self from the observed, stands in stark contrast to a failure that was not about a confused echo, but a complete and utter loss of time itself. Its most critical component was a master clock of unparalleled accuracy, an atomic timekeeper designed to tick with the unwavering rhythm of the universe. This clock was the silent conductor of the entire mapping orchestra, synchronizing every laser pulse, every radar echo, and every image capture. Without its perfect tempo, the precise location of every mountain and river would be lost. Yet this paragon of stability had a hidden, fatal sensitivity. It was vulnerable to the invisible tides of Earth's own magnetosphere. As the satellite passed through regions of shifting magnetic intensity, these subtle fields would pull at the clock's delicate internal physics, causing its frequency to drift in tiny, random, and utterly unpredictable steps. The clock was not broken, it was bewitched, its perfect rhythm corrupted by the planet's own magnetic song. On the ground, the effect was a cartographic nightmare. A mapping pass over the Amazon would be stamped with coordinates that placed it 100 meters to the east. A scan of the Himalayas would be slightly out of sync with the previous month's data, creating the illusion that a mountain peak had magically shifted. The maps were not just wrong, they were inconsistently wrong, a hall of mirrors where nothing could be trusted. This failure exposed a profound truth. You cannot build a map of space if you cannot correctly measure time. The quest for perfect timing had focused so intently on internal stability that it had forgotten the external environment. The solution required a fundamental shift in strategy. Engineers began hardening these exquisite timepieces against magnetic interference, shielding them in layers of special alloys. But the real breakthrough was admitting that no single clock, no matter how perfect, could ever be fully trusted alone. The new standard became a conversation in time. Satellites were equipped with GPS receivers, allowing them to constantly listen to the synchronized ticks of multiple atomic clocks in the much higher GPS constellation. The onboard clock was no longer the sole authority. It became one voice in a chorus, continuously checked and corrected against this external celestial metronome. We learned that true precision comes not from a single isolated master, but from a network of peers constantly comparing notes across the void. This hard-won synchronization with the cosmos itself, this ability to lock our orbital watches to a universal time, was the final, essential step in learning how to truly see our world. A subtle, almost imperceptible wobble became this satellite's signature flaw. Designed as a comprehensive observer, it carried a suite of instruments to create a unified portrait of both land and ocean, a mission demanding perfect stability. But a last-minute instrument swap before launch, a seemingly minor change, had introduced a tiny mass imbalance. One side of the spacecraft was ever so slightly heavier than the other. In the frictionless environment of orbit, that tiny asymmetry was enough to induce a constant, slow precession, a gentle wobble like a top beginning to tire. This wasn't a violent tumble, but a persistent drift that made precise pointing a nightmare. Its cameras, though mechanically perfect, could never hold a steady gaze. The resulting images were like puzzle pieces from different boxes, impossible to stitch together into a seamless map. Coastlines from one pass would not align with the same coastlines from the next. The data was a cartographer's frustration, a beautiful picture perpetually out of focus. Yet, wrestling with this uncooperative platform forced engineers to invent new solutions on the fly. They developed sophisticated dynamic balancing algorithms, software that could model the wobble in real time and fired tiny thrusters in a complex rhythm to counteract it. They pioneered the use of active mass trim systems, small movable weights inside the satellite that could be adjusted in flight to slowly shift the craft's center of mass and cancel out the imbalance. This persistent wobble taught a brutal lesson in the physics of precision. It proved that for a satellite to see the world clearly, it must first achieve a state of perfect internal balance. Every bolt, every instrument, every wire had to be accounted for, its mass and position known with absolute certainty. The quest to steady this one unsteady eye led to an unprecedented focus on mass properties management during assembly, turning clean rooms into scales of exquisite sensitivity. We learned to build observers that were not just mechanically sound, but gravitationally harmonious, a hard-won stability that stands in stark contrast to the violently chaotic end of our next subject. A silent, hypervelocity bullet written in the language of pure physics found its mark. An early and dedicated mapping satellite, performing its duties flawlessly, was suddenly struck by a small, untracked piece of space debris. This was not a dramatic explosion, but a brutal puncture. The impact did not destroy the satellite, but it severed a critical data bus, the main nervous system connecting its brain to its instruments, and shredded a section of one of its solar panels. In an instant, the vibrant cartographer was reduced to a limping survivor. Its power was crippled, its data throughput slowed to a painful trickle. It could still see, but its vision was blurred and its voice was a strained whisper, a ghost of its former self. This random act of cosmic violence was a terrifying wake-up call. The satellite itself became the most poignant piece of data, providing stark, undeniable evidence of the growing threat in low Earth orbit. Every strained transmission, every reduced power reading, was a real-time report on the consequences of a collision with an object no larger than a screw. The mission's primary objective was lost, but its new, unintended purpose was far more valuable. Engineers pored over the damage reports, using them to design a new generation of armored satellites. They began incorporating redundant, physically separated data buses, so a single impact could not sever all communication. Solar panels were redesigned with stronger substrates and interwoven circuitry, making them less vulnerable to a single, catastrophic tear. Most importantly, this failure added a desperate urgency to the nascent field of space traffic management. It proved that we could no longer simply launch satellites and hope for the best. We had to start mapping the void itself, tracking the countless fragments of our own technological litter. This single impact accelerated the development of global debris tracking networks and sophisticated collision avoidance systems, transforming our approach from one of hope to one of active defense. We learned through this violent lesson that to map a world, we must first learn to protect the mappers from the invisible shrapnel of our own ambition. A final, sobering lesson in survival that brings us to our last and perhaps most poetic failure. A perfect cartographer became a digital ghost. This final satellite in our chronicle did not break, spin, or fall silent. It performed its primary mapping mission with brilliant, uninterrupted success, delivering every image and measurement it was designed to capture. Its data was pristine, its instruments flawless, yet within a single decade of its mission ending, its entire legacy was locked away in a vault with no key. The data format it used was proprietary, owned by a single corporation, and the ground processing software needed to translate its raw numbers into usable maps was poorly documented, built on forgotten code. The satellite had not failed technology, it had failed time. Its perfect record became a digital Rosetta Stone that no one could read, a library of our world rendered into a language that had become extinct. This was a success that failed, a triumph that turned to dust. It taught a painful meta lesson about the fleeting nature of knowledge itself. What good is a map of the world if you cannot open the scroll? This final, obscure failure forced a fundamental change in how we think about the future. From that point on, the true success of a mission was measured not just by the data it collected, but by its accessibility for decades, even centuries to come. It led to the now universal standard of using open, well-documented, non-proprietary data formats. Raw data, processed data, and the software tools to read it all are now archived in public, enduring repositories, a gift to future generations of scientists. The satellite that succeeded too perfectly in its own brief moment ensured that every success that followed would be built to last, its story written not in temporary code, but in the permanent language of open science. And so, our map of 24 missteps is complete. Each obscure failure, from the first tumbling probe to this last digital ghost, was a hidden compass point. They did not lead us away from our goal, but directly toward it. Every broken part, every silent satellite, and every flawed calculation was a lesson in disguise, a brutal but essential tutor. Together, they forged the resilient, precise, and enduring eyes that now watch over our planet. The clearest views of Earth were not born from a straight line of perfect launches. They were carved from the hard stone of experience, each failure a chisel stroke that brought our world into sharper focus. These 24 scattered mishaps form a single, hidden blueprint. Look closer and you see a pattern emerging from the chaos, a coherent curriculum for building a better eye in the sky. Each failure was not a random accident, but a targeted strike on a different fragile assumption. We assumed our platforms would be stable, and a tumbling satellite taught us to filter out spin. We assumed power was a simple matter, and a silent cartographer taught us the ruthless necessity of redundancy. We believed communication was straightforward, until a data glutton taught us to speak a more efficient language. This relentless pressure from reality tested every single subsystem, from the software brain to the mechanical limbs, from the thermal heart to the magnetic soul. The cumulative effect of these tests was a transformation. Orbital mapping was no longer a hopeful art, a gamble on a perfect launch. It became a predictable, efficient science. We learned to anticipate the unexpected, to build systems that could not just survive failure but learn from it. This entire tapestry of errors, woven together across decades, is what created the resilient, precise, and powerful global mapping network we lean on today. When scientists track the relentless creep of sea level rise, when urban planners model the growth of a megacity, when first responders race toward a hurricane's aftermath, they are using tools forged in the fires of these 24 obscure failures. The greatest maps, it turns out, are not just charts of continents and oceans. They are also a record of the arduous, invisible journey we took to learn how to see. Our most precise maps of Earth stand upon a foundation of stumbles and forgotten miscalculations. Not one of those 24 broken missions was a wasted effort. They were the essential tuition, the price paid for a world-class education in how to observe our planet from the void. This hidden history proves a powerful truth. In the grand pursuit of futuristic technology, there are rarely true dead ends. Instead, we find a landscape of unexpected detours, winding paths that often lead to far better destinations than the one we originally charted. So the next time you look at a satellite image, tracing a coastline or navigating a city grid, try to see more than just the land and the sea. See the legacy of the silent cartographers who taught us about resilience. See the blurred vision of the myopic imagers who taught us to see through the atmosphere. See the chaotic dance of the tumbling satellites who taught us how to find stability within the spin. Let this entire chronicle of productive failure inspire you. Your own endeavors, whatever they may be, will inevitably involve setbacks. The goal is not to avoid them, but to learn their language, to understand that every broken part can contain the blueprint for a better solution. If this journey through the hidden stories behind our modern world resonated with you, be sure you do not miss our next deep dive by subscribing to the channel. And we would love to hear which of these 24 obscure failures surprised you the most. Share your thoughts in the comments below.